TPU is underrated. So in this video, I'll explain what TPU actually is, show you how to print without the headaches, test new materials like 2.2mm and glass fiber reinforced TPU, and finish with a range of applications I bet you haven't seen before. Let's get right into it here at JanTec Engineering. Thanks to Prusa Research for sponsoring my studio. It was a bit of a pain the last few weeks, hitting over 40 degrees in here, but I'm still super grateful to have a dedicated workspace for my projects. Depending on when you got into 3D printing, you might have some bad memories of TPU. I remember trying to print it on my Prusa Mini when it launched, and it was a nightmare. The filament kept tangling at the Bowden extruder. TPU flips a lot of what PLA taught you. But things have changed. Most modern printers come with a direct drive extruder, which makes flexibles much easier, and there are new print sheets and modified TPUs on top of that. This video is meant to be a guide on how to print TPU and what to use it for. But first, we need to understand what TPU actually is. TPU stands for thermoplastic polyurethane. It's part of a larger family called thermoplastic elastomers or TPEs. Every TPU is a TPE, but not every TPE is a TPU. The number you'll see on every spool is the Shaw hardness. That's how the flexibility is specified. Most flexible filaments use the Shaw A scale, which runs from 0 to 100, and lower means softer. To get a feeling for the scale, Shaw 0 is often compared with jelly candy, and D100 is the maximum hardness on the scale, like a bowling ball. The most common hardness in FDM filament is 95A, which can be found in everyday items like shopping cart or skateboard wheels. Keep in mind, the hardness number is a material property, but how flexible a printed part actually feels also depends on its geometry. A thin wall of 95A bends easily, a solid block of the same filament barely moves. We'll come back to that when we talk about applications and design tips. There is a huge variety of TPEs on the market. There are special brand names, different Shaw hardnesses, and modifications like fillings. I collected many different spools over the last years, and I will put links to all the filaments shown here in the description. When trying to print TPU, there are basically only three things that tend to go wrong: moist filament, wrong speed or temperature slicer settings, and bad adhesion. That's basically it. So let's go through it step by step. TPU is hygroscopic, which means it absorbs moisture from the air. When that wet filament melts in the hot nozzle, the water turns into steam. That leads to bubbles and stringing, ruining the visual appeal and strength of your prints. I dried all my spools using the Sunlu S4 set to 60 degrees C for 6 hours with some silica gel in it. An oven works too if you don't have a dedicated filament dryer, just make sure to not melt the filament and spool into one giant blob. After drying, you have to keep it dry while printing, because it will start reabsorbing moisture almost immediately. Easiest option is to print straight out of your dryer, or put a spool into a sealed, passive dry box like the Prusa USS Drybox. Or honestly, if your room isn't super humid, just dry it and print it right away like I did most of the time. And the key thing to understand, how much moisture a TPU absorbs and how much that moisture actually degrades it, comes down to its chemistry, not its Shaw number. The backbone can be ester, ether or carbonate, and that's what determines the behavior. Two spools can both be rated 95A and act completely differently. An ether-based grade like Prusament's TPU-95A absorbs very little, for example. Some datasheets list a moisture absorption number. You can treat it as a rough "how careful do I need to be" rating. Slicer settings are also fairly easy. Most filament manufacturers provide dedicated print profiles for major slicers, so just select it and start printing. If you still have problems, there are two parameters worth looking at. First is speed. Most TPUs need to be printed slower, otherwise the filament can buckle in the extruder. But instead of tweaking all the velocities and accelerations manually, there is an easy hack: max volumetric flow rate. Lower it and the slicer automatically caps all other values. No manual speed tuning needed. The second setting is a nozzle temperature, and I'd recommend printing a temp tower. Changing nozzle temperature by just 10 degrees can have a large effect on print quality, especially if the filament isn't completely dry. Last but not least, there's bad adhesion. With most other filaments, the problem is getting them to stick and not warp. With TPU, it's the opposite. It usually sticks too well and you can easily damage your print sheet when you remove the part. That's why you have to choose the right sheet and maybe even use a release agent. Prusa has a recommended sheet list, so you can just pick one of those or use smooth PI with glue stick as a release agent. The glue layer is what releases, so the TPU bonds to that instead of directly to the coating. I personally had good results on the satin sheet. If a print still sticks too well, you can put the whole sheet in the freezer for a few minutes. TPU and the steel sheet contract at different weights, so the part pops off. With all that in mind, you shouldn't have any trouble printing TPU. And if this helped, consider subscribing to my channel. Most people watching aren't yet, and it really helps me out. Thank you. If you know this channel, you know I usually test every filament on my own mechanical testing setup. For this video, I decided against it because Stefan from CNC Kitchen already made a very good video testing a wide range of TPEs. Link is in the description. All in all, TPU is characterized by excellent layer adhesion and massive yielding before failure, making it highly resilient under tension and impact. Before we continue with 2.2mm and glass fiber filled TPU, a few words about the sponsor of today's video, PCBWay. Did you know PCBWay is more than a PCB manufacturer? Beyond advanced PCBs, they also do CNC machining, 3D printing, sheet metal and injection molding. Just upload your design to PCBWay.com, pick your manufacturing options and get an instant quote. For me, PCBWay is the one-stop shop for all the parts I can't manufacture in my home lab. Right now, I'm ordering CNC machined steel and aluminum parts for my DIY universal testing machine, plus some PCBs for personal projects. I really enjoy their instant quotes, real-time order tracking and fast delivery. If you're working on something complex and need professional grade manufacturing with short lead times, check out the link in the description. Thanks to PCBWay for supporting the channel. Now back to the TPU. At Formnext 2025, Recreus introduced something I found genuinely interesting, 2.2mm TPU. Here's the idea. As already mentioned, TPU usually has to be printed slowly. It's soft, so it can buckle on its way through the extruder and filament path, and that buckling potential is what limits the speed. So Ignacio, the CEO of Recreus, had a simple idea. Make the filament thicker. Going from 1.75 to 2.2mm doesn't sound like much, but cross-sectional area scales with the square of the diameter, so that's about 58% more material in the strand. And that's what increases buckling resistance. It feeds more reliably, which is what lets you push the speed up. Instead of going all the way to the known 2.85mm, they settled on 2.2 as a sweet spot. It still works with extruders and PTFE tubes built for 1.75mm filament, only the hot end and nozzle need to be swapped. And since the new nozzle still runs regular 1.7 filament too, you're not locking yourself into 2.2. Recreus was kind enough to send over 2 nozzles and 3 spools of their 2.2mm TPU for me to try. I wanted to dedicate the whole video, but I only have capacity for 1 video a month, so I'm covering it here. The only thing physically required is the nozzle swap. The special nozzle has a wider tube to fit a thicker filament and is a little lighter than the original Prusa nozzle. It's installed in a few minutes. That's it on the hardware side. Then you download their slicer profiles and import them into Prusa Slicer. I started with a Benchy, only to find out the filament out of the box was wet. Lowering the temperature didn't fix it, so I dried it for a few hours, put it in my Fiberthree Drybox and finally got clean prints. I printed a set of feet I designed and it came out in about half the time the regular profile suggested. Of course, you could probably tune the standard 1.75 profiles for more speed too, so a fair comparison would need a dedicated speed printing test. Looking at you, 24/7 printing. But as a first impression, this worked well, and I think it's really interesting if you're printing TPU on a bigger scale when print time matters. If you want me to dive deeper into this filament, let me know in the comments. The next special filament is glass fiber reinforced TPU. I first saw this at the Japan Wrap-Up Festival and covered it briefly in my video about the event. A lot of you in the comments were excited about this, so I reached out to JanTec and asked if they could send me a spool. They did. First impression out of the box, it's really interesting. It's flexible, but it looks and feels like a filled material. It loads through the PTFE tube on the printer like normal filament. So let's do such a test print. The printer prints as usual, and removing the print from the satin sheet was really easy. Bending it, you can see that it's flexible but still stable. The surface is what surprises me. Normally, a fiber-filled filament gives you that rough, textured finish, like this glass fiber-filled nylon here. The TPU-GF doesn't. It looks like a fiber-filled print, but the surface feels normal and quite smooth. It's hard to describe until you have it in your hand. That combination, flexible but tough, is what makes it interesting for things like bumpers or sturdy parts on a battlebot. So why does this work? The glass fibers are stiff and strong but brittle on their own. The TPU bonds to the surface of each fiber and grips it. In fact, Lost in Tech made a detailed video on it with some great macro shots of the fibers in the print, link in the description. So what would you print with TPU-GF? Let us know in the comments. Now let's finally get to some sample applications along with a few design and slicing tricks. As I said earlier, shore hardness is a material property. The final geometry decides how flexible the part actually is. Of course, there are standard parts like bumpers, phone cases, rubber-like feet for machines and furniture. All these are useful, familiar, and there are plenty of ready-made STLs online, so you don't even have to design them yourself. Most people associate TPU with soft prints, but the softness or flexibility comes from geometry, so with enough walls and infill you can print rigid yet tough parts. I made this motor mount from Prusamet 95A TPU using a 0.6mm nozzle and 100% infill. Christopher Helmke, for instance, printed gears in TPU for his screw counting machines. The gears run smooth and silent with minimal motor vibrations. He said that it basically eliminated teeth breaking off from the gears. With the TPU-GF from JanTec, you can go even further with rigid TPU prints. Next, there are material combinations, and this is where it gets really interesting. Tool changers are getting more accessible. We have the Prusa XL, Snapmaker U1, the Bondtech Index, and more coming up. That makes combining a rigid filament with TPU practical. I made this phone case with a hard PETG outer shell and a soft TPU inner shell printed in one go. But there's a catch. TPU doesn't chemically bond to all filaments. A good fix is interlocking, a mechanical construction where the two materials physically lock together instead of relying on adhesion. Since version 2.9.1, Prusa Slicer does it for you. It builds a cross-hatched beam structure at the material transition, so filaments that normally won't stick, like PLA and TPU, hold together mechanically. This is great for education models or functional parts like hinges. Instead of only combining TPU with other materials, you can also use PLA as a support material for TPU prints, like for these printed bellows. Functional Print Friday has a clever method here, printing TPU and PLA in alternating layers, then peeling the PLA away to leave a clean folded bellows. Useful as a dust cover over a linear rail, for example. I printed one myself, and I've been designing my own smaller bellows for my universal testing machine. I haven't taken that as far as I'd like yet, but once they are fully parametric bellows, it opens up a huge range of applications. Lastly, I didn't want to leave 3D printed fashion unmentioned. There are a lot of free designs for shoes, bags and purses. On the commercial side, Zellerfeld prints entire shoes from TPU on FDM machines, a whole shoe as one recyclable part. If you want more inspiration, Igor from My Tech Fun made a video asking a bunch of us 3D printing creators about our favorite TPU prints. I highly recommend it, link is in the video description. And finally, I'm genuinely interested in your TPU prints. Describe them in the comments or share them on X and tag me. Thanks for watching. Also, a huge shout out to my channel members. See you in the next video here at JanTec Engineering.